Hello everyone. So this lesson is going to be lesson 11. So the second last lesson in this unit on average rate of change. This lesson was originally supposed to be in the rational functions unit, but we had taken it out before March break so that we could finish that unit in time to do our test before March break. So a lot of this is kind of going back to looking at our polynomial and our rational functions. There is a little bit on logarithmic functions here. But for the most part, it's all older stuff. If you're, I guess actually, we'll start off by defining what rate of change means. So rate of change we're looking at the rate of change how much we're changing over an interval of domain. So average change per unit of our domain. So in the first example, we have a graph that looks like this. So I've drawn out the graph that's in your notes or in the completed note. And so what they tell us about this graph is Billy's mother sends him to the corner store for milk and tells him to be back in 30 minutes. What is the average rate of change for the different sections of Billy's trip? So I've drawn out and listed all the important points that we're going to look at. We can see there's a number of different slopes to the lines of the parts of the trip. So we're going to look at every single example, every single different slope of these lines. So we'll divide it into 5. There's 5 unique parts of this graph. So to start off, our rate of change, we're really just looking at those slopes. So rate of change is the rise over the run. If we remember back to grade 9, linear equations, or, delta rise is delta y, run is our delta x. So for our first section, we're starting at, so the first section is going from 0, 0 to 4, 200. And so our x, it tells us is time in minutes. Our y is the distance from home in meters. So that first section of the trip, we would calculate the rate of change, or the ROC for short, is the rise. So how much we're increasing in y. So we're increasing 200 meters in this case. So we're increasing 200 meters. And then our run, how much we're moving left and right, we're going over 4 minutes. So that average, from 0 to 4, we get 4 minutes. So 200 divided by 4 is 50. And our units we have meters divided by minutes. So he's going 50 meters per minute. Similarly, we can look at any of these other sections. So we can go look at section 2. So section 2, we're going from the point 4200 to our new point 12400. So how much are we rising? What is the rise and run of this in order to find our rate of change? So we're rising from 200 to 400. So 400 minus 200, we're rising 200 meters. We're running from 4 to 12. So 12 minus 4, we get 8. We're going 8 minutes for this stretch. So Billy's traveling 200 meters in 8 minutes for the second part of his journey. 200 divided by 8 is 25. And again, our units are going to be 25 meters per minute. The first 4 minutes, he's going 50 meters a minute. Now the next 8 minutes, he's going 25 meters a minute. We can see that slope, that section of line, its slope is less steep. That tells us we're going less quickly. We're traveling at a slower speed. We're only going 25 meters per minute now. In the notes, they also calculate this third section all the way from 12,400. So he'd gone 400 meters in that first 12 minutes until he gets to the store, which is 800 meters away after 16 minutes. You can look there to look at that example. Also in the notes, it shows section 4. So why don't we show section 5 here? So section 5, we're starting at 28,500 and we're finishing at 40,000. So the rate of change for this section, we're going from 500 to 0. So we're subtracting our first value from our second one. So if you remember the formula for slope, y2 minus y1 over x2 minus x1 for that rise over run. So our second y we do first minus our first y. And then it takes from 28 to 40 minutes. So we're going to do 40 minus 28. And so that's going to give us negative 500 over 12. Negative 500 meters over 12 minutes. Negative 500 divided by 12 is approximately negative 41.7. And again, this is meters per minute. So what does it mean to have a negative rate of change? That means as we're moving left to right, same as a negative slope, our y value's decreasing. He's getting closer to home, so his distance from home is going to decrease all the way from 500 till he's at home. He's 0 meters away from home. So this positive rate of change, a positive slope, is Billy getting further away from home. This negative rate of change, this negative slope, we're getting closer to home. So That's a negative rate of change is telling us that our function is decreasing. A positive rate of change is telling us that our function is increasing. So rate of change when we're talking about linear equations is fairly straightforward. This is something that we've been doing since grade 9 formally, and even before that you would have talked about the idea of ratios and rate of change in middle school. We'll look at what rate of change looks like for these nonlinear graphs now. So to find the average rate of change, on a nonlinear graph, we choose 2 points of the graph that represent the endpoints, or like a beginning point and an endpoint of our chosen interval. And from there, we draw a secant line. So a secant line means if we have a curve, we go look at those beginning and end points, the endpoints of our interval, and we draw a line through those 2 points. So a secant line is a line that crosses a curve at 2 different points. You may have also heard of, that's a secant line. You may have also heard of a tangent line, and that's when it crosses a curve at just 1 point. So a tangent line just touches a curve. A secant line crosses that curve at 2 different points. And we'll talk about both those in the next 2 lessons. So we're drawing a secant line. And we then find the slope of the secant. In order to represent the average change in the independent variable the note says independent variable. It should say in the dependent variable. So it's the change of the dependent variable for each unit. And remember, rate of change, we were talking about units in the domain. So each unit in our independent variable. So we're using these same strategies we use to calculate the slopes of all these different parts of this line. We're going to use those on the secants that we draw through our curves. So we'll look at what does this necessarily look like. Our first example, we have this graph here. Parts of it got slightly erased. And so this question asks, determine the interval determine the average rate of change. This is example 2. Determine the average rate of change on the interval x. 3 is less than x. Less than or equal to x is less than or equal to 5. So again, in interval notation, that would be x an element from 3 to 5. We're interested, what is our average rate of change there? So all our different points are labeled. I've gone ahead and labeled them for us just so it's a little clearer because I'm drawing this on a whiteboard and not graph paper. Our first point we're interested in is this. We're starting from x equals 3, so this point 3, negative 2. We're also interested in this point 5, 6. We want to see what is the average rate of change from this point to this point. So we're going to go ahead and draw our secant line. We're going to use our handy ruler here. Maybe. We're going to draw a line. Not the best. We're going to draw a secant line, so a straight line from those 2 points. And that secant line, that line that crosses through those 2 points, we now are interested in what is the slope of that line. So slope, as always, is that y2 minus y1 over x2 minus x1, or now that we've learned other ways to talk about functions, it's f of x2 minus f of x1 over x2 minus x1. This is the grade 9 version. This is now that we're in grade 12 and we're used to that f of x notation. This is how we'd write that same statement. But we're still doing rise over run. So our second f of x is 6. Our first f of x was negative 2. So we're coming from 6 and negative 2. So 6 minus negative 2 over our x values. X equals 5 minus x equals 3. 6 minus negative 2, same as 6 plus 2, we get 8. 5 minus 3, we get 2. And 8 divided by 2, we get 4. So 4 units of y for every unit of x. So the average rate of change is every time we go over by 1, we're going to go up 4 units. So if we were at 3, negative 2, this point here is now at 4, positive 2. We've gone up 4 units from negative 2 to positive 2. And then we go over 1 unit in the x, and we go up 4 units in the y. We go 2, 3, 4, 5, 6. We go up 4 units to 6. And the average rate of change from x equals 3 to x equals 5 is 4. Look at another example here. This will be our third example using graphs. And in this question, the graph relates the speed of the wind in miles per hour near the center of a tornado to the number of miles that the tornado travels. They don't necessarily tell us which is which. But So we have to be able to decipher that a tornado's wind speed will depend on miles traveled and not the other way around. How far a tornado travels doesn't depend on its wind speed at any given time. So this has to be our independent variable. This wind speed has to be our dependent variable. Determine the average rate of change for the speed of the wind at the center of the tornado as it traveled from mile 10 to mile 60. And I believe in the original note it says 120. This graph doesn't go up to 120, so we've changed that to 60. So we're looking at the rate of change of wind speed from mile 10 to 60. So I've already gone ahead and labeled these points because, again, they're hard to see on this whiteboard. So mile 10, we have a wind speed of 160 miles per hour. Mile 60, we have a wind speed of 230 miles per hour. So on the graph, in order to actually see that, we're looking at mile 10. We're going up from mile 10. And of course, that should be straight up from mile 10 here. And then we go across, and on the graph, in your note, it's much easier to see this is at exactly 160. So that's how we're going to find our y value. And we would do the same for this one. We go up from 60, go across, and we'll see that it's at y equals 230. Once we have those 2 points, we're finding, so we're going to draw the secant between those 2 values. So we're going to draw a nice, perfectly straight line between those 2 points. And now we're interested in what is the slope between those 2 points. So what is our rate of change? What is our slope? So again, it's that y2 minus y1 over x2 minus x1, or f of x2 minus f of x1 divided by x2 minus x1. Our second y value is 230. Our first y value is 160. Our second x value is 60. Our first x value is 10. 230 minus 160 is 70. So that's 70 miles per hour. 60 minus 10 is 50. And again, those units are miles. So 70 miles per hour divided by 50 miles . 70 divided by 50, or 7 over 5, gives us 1.4 miles per hour divided by miles. Some of you who've taken physics will be a little more used to units canceling out. This is completely acceptable for us to write. We're not as concerned about units in this case. We're more concerned with this concept of rate of change. But if you are comfortable with that, you might realize miles per hour, miles divided by hours divided by miles, those units are going to cancel out. And so we really just get hours, or hours to the -1. If you want to simplify those units, you're definitely allowed. But this is really all we're expecting for this type of problem, is you can leave it like that. So you do not have to simplify your units. If you have no idea what I did here, that's okay. That's not what I'm worried about at this stage. So if we were to talk about what this actually means, so therefore every mile the tornado travels, the wind speed at the center of the tornado increases by 1.4 miles per hour. And now that I'm looking back at it, these miles are completely different than these miles. This is the miles that tornado is traveling. This is the miles, how many miles per hour the wind is traveling. So this doesn't even make any sense. These miles are not related. I didn't take the time to actually think about the problem, so completely ignore that part from before. So that would be a suitable answer for that question. That's finding rate of change from graphs. We're going to look a little bit at how we can now go through average rate of change using table of values. So let's get a new sheet of paper. This is the second page of this note that you'll find online. So finding average rate of change from a table of values. As air is pumped into an exercise ball, the surface area of the ball expands. The table shows the surface area at 2-second intervals for 20 seconds. Calculate the average rate of change. So calculate average rate of change for, so we're doing the first 10 seconds. So I'm going to write an abbreviated version of this graph, or sorry, not graph, table of values. So we have time in seconds, and we have the surface area in centimeters squared. We start off after 0 seconds. The surface area is 10 centimeters squared. After 10 seconds, our surface area is 324 centimeters squared. And finally, after 20 seconds, our surface area in the table of values on the note tells us that we're 1,266 centimeters squared. So again, anytime we have a table of values, our independent variable, our x is almost always by convention listed on the left. Our dependent variable, so in this case surface area, is listed on the right. And we don't necessarily need to know anything about these numbers in between. So I haven't written them down from 2, 4, 6, and 8 seconds and our corresponding surface areas. They're not important to us. We only care about the secant line on this graph from 0 to 10. Nothing in the middle matters. So if we're calculating this rate of change, again, we're seeing what is the slope from 0 to 10. So our y values change from 10 to 324. And our x values, the time, goes from 0 to 10 seconds. So we're looking at the first 10 seconds. 324 minus 10 is 314. 10 minus 0 is 10. And 314 divided by 10 is going to be 31.4. So because this was centimeters squared and this was seconds, our rate of change, our average rate of change, is going to be 31.4 centimeters squared per second. So that means on average, in each second, each of the first 10 seconds, the surface area of the ball increases by 31.4 centimeters squared. So on, not necessarily every second, some seconds it increased more than that, some it increased less than that, but on average for those first 10 seconds, in order to get from 10 to 324, we need to go up by 31.4 centimeters squared every single second. In the last 10 seconds, so we end up at 20. So from 10 to 20 we're looking at. We're going to do the same thing. This time I'll write it with our function notation. So f of x2 minus f of x1 over x2 minus x1. So that's the exact same thing as y2 minus y1 over x2 minus x1. Our y, or our f of x, we end up at 1266. So our final value is 1266. We started, our initial value is 324. And we're going from 10 seconds to 20 seconds. So 1266 minus 324 is 942. 20 minus 10 is 10. Again, this is centimeters squared and seconds. So that's going to be 94.2 centimeters squared per second. So again, this is on average, not necessarily every single second, but on average, in each of the last 10 seconds, the surface area of the ball, we're still increasing because it's positive, but that surface area is going to increase by 94.2 centimeters squared every second on average. So that's how we would find rate of change from a table of values. Again, we're doing the exact same thing. We're only looking at our initial value and our final value, and we're seeing what is our rate of change from those two values. What is our slope if we drew a straight line between those two values? Finally, finding rate of change from an equation. Finding our average rate of change from an equation. So reminder, average rate of change, we're looking at the slope. So we're looking at rise over run, y2 minus y1 over x2 minus x1, or f of x2 minus f of x1 over x2 minus x1. So we're still doing the exact same thing, but we're going to need the equation to find out what some of these values are. So because we've been talking about logs, we're going to look at a log example. For the previous tornado example, the function they give us, w of d equals 93 log d plus 65. So that equation relates the speed of the wind, w, in miles per hour near the center of a tornado, to the distance, d, that the tornado travels in miles. We're doing the same thing. Calculate the average rate of change for the speed of the wind at the center of the tornado from mile 10 to mile 60. So average rate of change, we're looking at the change in our y compared to the change in our x. So in this case, our function is w. That's going to tell us what our change in our dependent variable is, and our independent variable is d. So looking at the change in w divided by the change in d. So our final wind speed minus our initial wind speed divided by our final distance minus our initial distance. And because we're going from 10 miles to 60 miles an hour, we're going to go from, our D2 is going to be 60, and our D1 is going to be 10. So W of 60, we're plugging in 60 into D. So 93 log, our D is 60, plus 65. Minus W of 10, we're plugging D equals 10 into the equation. 93 log 10 plus 65. And 60 minus 10 is 50. So 93 log, no base is written, so it's base 10. We can just plug it right into our calculator. 93 log 60 plus 65 is 230.37. 93 log 10 plus 65 gives us a nice round 158 over 50. 230.37 minus 158. 72.37 divided by 50 gives us 1.4 1.4474. What are our units? Our top was all wind speed. So this is talking about miles per hour. Our bottom was distance. This is miles. So 1.4474 miles per hour per mile. So therefore, in each of the 50 miles traveled, so we went from 10 miles to 60 miles, so each of those 50 miles, the tornado's inner wind speed increased, because we're positive rate of change, by approximately 1.45 miles per hour per mile. Oh, we already talked about per mile. So in each of those 50 miles, the tornado's inner wind speed increases by about 1.45 miles per hour. And we can use this exact same method for any type of function. So we'll look at a polynomial example. So for polynomials, the thickness on the ice on a lake for the first week of a new year is modeled by this function, T of D equals negative 0.1 D cubed plus 1.3 D squared minus 4.4 D plus 14.8, where T of D is thickness of ice in centimeters, and D is the number of days since December 31st. How is the thickness of the ice changing over the first 3 days in January? So January 1st would be the first day. January 2nd would be the second day. January 3rd would be the third day. So we're looking from when we're starting to the third day after December 31st, January 3rd. So we're looking from D equals 0 to D equals 3. What is our rate of change for those 3 days? So again, we're really looking at the slope, the change in y over the change in x, the rise over the run. So we're looking at the change of our function t compared to our change in our variable d. So what is t of d2 minus t of d1 over d2 minus d1? So t of 3 minus t of 0 over 3 minus 0. So t of 3, we're plugging in 3 into our function t. So minus 0.1 times 3 cubed plus 1.3 times 3 squared minus 4.4 times 3 plus 14.8 minus, for the sake of room, I'm going to have you look, if we plug in d equals 0 into this equation, this whole term becomes 0, this whole term becomes 0, this whole term becomes 0, so we're just subtracting this 14.8. T of 0 is just 14.8. The amount of days we're doing this for, 3 minus 0, is 3. So we need to calculate what is t of 3. So negative 0.1 cubed plus 1.3 times 3 squared minus 4.4 times 3 plus 14.8. 13.299 minus 14.8 over 3. Did I do that right? Oh no. Sorry. Minus 0.1 times 3 cubed plus 1.3 times 3 squared minus 4.4 times 3 plus 14.8. That's 10.6. So 10.6 minus 14.8 over 3. 10.6 minus 14.8 is minus 4.2 over 3. T was thickness in centimeters. D was number of days. So negative 4.2 centimeters divided by 3 days. 4.2, negative 4.2 divided by 3 is negative 1.4 centimeters per day. So for the first 3 days in January, the ice is decreasing because we have a negative rate of change. The ice decreases in thickness by 1.4 centimeters per day for the first 3 days in January. And again, this is on average for those 3 days. So first unit polynomials, we can find the rate of change of polynomials still by just plugging in our values into the equation. And we can do this with rational functions from our second unit as well. So rational functions, example. This is the last question in the lesson. The snowshoe hare population in a newly created conservation area can be predicted over time by this equation, by this model. P of t is 2,550 t squared plus 1,250 over 25 plus t squared. So P is population. And T is time in years. Calculate the average rate of change in the hare population between, so rate of change in population from (10 to 15 years. So we're looking at the change in our population divided by the change in time. So P of 15 minus P of 10, our final minus our initial, divided by our T2 minus T1. So P of 15, 2550 times 15 squared plus 1250 over 25 plus 15 squared minus P of 10, 2550 times 10 squared plus 1250 over 25 plus 10 squared. So we have this giant ugly numerator all over, this is all of our numerator, divided by 15 minus 10, divided by 5. We're going to slowly simplify this. 2550 times 15 squared plus 1250 is 575,000 over 25 plus 15 squared, 250 minus 2550 times 10 squared plus 1250 is 256,250 over 25 plus 10 squared, 125. Again, this is all over 5. 575,000 divided by 250 is 2,300 minus 256,250 divided by 125 is 2,050 over 5. 2,300 minus 2050 is 250. 250 divided by 5. And 250 divided by 5 is going to be 50. So this whole mess up here gets us all the way down to 50. Again, our numerator is population, so 250 hares. We're talking about hares, right? Snowshoe hares, yes. Our bottom was time. We're talking about years. So this is 50 hares per year. And I noticed there's a typo now in the notes. In the notes, it's written down this should be 10 years. 15 minus 10 is most certainly 5 and not 10. So this is a correction here. So that means for the 5 years, the hare population increases because it's a positive rate of change by 50 hares per year on average. That's the end of average rate of change. I've got one more lesson to upload on instantaneous rate of change. After that, I recommend going through some of the unit review. Make sure you've been going through homework and just feeling comfortable with the types of questions that could be asked. In case we do end up back in school, this will be on the exam. You will have assignments either way based on these questions, so make sure you're feeling comfortable with it. If you have any questions, please don't hesitate to ask. But overall, hope all is going well, and you'll hear from me in the next lesson. Have a good day and bye.